The universe is a vast and enigmatic place, teeming with celestial wonders. From swirling galaxies to collapsing stars, the universe is a cosmic ballet of creation and destruction. Black holes, those cosmic monsters, devour everything in their path. But what if there's another player in this cosmic arena? Enter the Gravastar, a theoretical alternative to black holes. Gravastars offer a tantalizing alternative, a cosmic haven where matter and energy are balanced. It becomes a Gravastar, a spherical shell of exotic matter. The concept emerged from physicists Pavel Mazur and Emil Motola in 2001. Gravastars challenge our understanding of the universe in profound ways. How do we distinguish a Gravastar from a black hole? Let's uncover the key differences between these celestial titans. Imagine a cosmic dance floor. On one side we have the black hole, a cosmic heavyweight, a master of gravity, pulling everything towards it with irresistible force. On the other side we have the Gravastar, a more enigmatic dancer, a master of balance, holding its own against the relentless pull of gravity. Both are born from the death throes of massive stars, but their fates and the ways they interact with the universe are dramatically different. Black holes, as we currently understand them, are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars exhaust their nuclear fuel and collapse under their own gravity. This collapse creates a singularity, a point of infinite density at the heart of the black hole, shrouded by an event horizon, a point of no return beyond which nothing can escape the black hole's gravitational pull. Think of a black hole as a cosmic vacuum cleaner, relentlessly sucking in anything that gets too close. Gravastars, on the other hand, offer a less extreme, albeit equally bizarre alternative. Instead of a singularity, imagine a cosmic bubble, a spherical shell of exotic matter held together by a repulsive gravitational force. This shell encloses a region of space-time that is essentially a vacuum, a void where gravity's pull is counteracted by the repulsive force of the exotic matter. Think of a Gravastar as a cosmic pressure cooker holding its contents in a delicate balance. The key difference between black holes and Gravastars lies in their density. Black holes are thought to possess infinite density at their singularity, a concept that has puzzled physicists for decades. Gravastars, in contrast, have a finite density, albeit one that is still incredibly high. This difference in density has profound implications for how these objects interact with the universe, particularly when it comes to light and other forms of radiation. While black holes are notorious for trapping light, Gravastars are predicted to interact with light in a more complex way. Instead of being completely absorbed, light passing close to a Gravastar would be bent and distorted by its intense gravity. This distortion could create a distinctive signature, a telltale sign that could help us distinguish Gravastars from their black hole counterparts. To understand the bizarre anatomy of a Gravastar, we need to journey to the heart of a dying star, a cosmic crucible where gravity and quantum mechanics collide in a spectacular display of energy and transformation. Imagine a star much more massive than our own Sun. Nearing the end of its life, its nuclear fuel spent, the star can no longer generate the outward pressure needed to counteract the inward pull of its own immense gravity. As the star's core collapses, its density skyrockets and the very fabric of space-time begins to warp and distort. According to the Gravastar model, this extreme gravitational collapse triggers a quantum phase transition, similar to the way water changes into ice. This transition transforms the collapsing star into a state of ultra-high density, but instead of collapsing into a singularity, the star's core undergoes a radical transformation. A new force emerges, a repulsive gravitational force generated by the exotic matter created during the quantum phase transition. This repulsive force halts the star's collapse, preventing it from forming a singularity. Instead, the collapsing star forms a spherical shell of this exotic matter, a cosmic bubble held together by a delicate balance of forces. This shell of exotic matter is the defining feature of a gravastar. It's important to note that the exact nature of this exotic matter remains a mystery. Some theories suggest it could be composed of particles not yet observed in particle accelerators, while others propose it could be a manifestation of the quantum vacuum itself, the seething sea of virtual particles that permeates all of space-time. Inside this shell of exotic matter lies a region of space-time that is essentially a vacuum, a void where gravity's pull is counteracted by the repulsive force of the exotic matter. This void, however, is not empty in the traditional sense. It's theorized to be filled with a form of dark energy, the mysterious force that drives the accelerated expansion of the universe. The boundary between the shell of exotic matter and the vacuum interior is a region of intense gravitational forces and quantum effects. It's in this region where the fate of information falling into a gravastar, a key question in the information paradox, would be decided. Section 4. The information paradox. Can gravastars solve the cosmic puzzle? The information paradox is one of the most perplexing mysteries in modern physics. It arises from the clash between general relativity, our best theory of gravity, and quantum mechanics, our best theory of the subatomic world. At the heart of this paradox lies the question of what happens to information that falls into a black hole. According to quantum mechanics, information cannot be destroyed. It might change form, but it's always conserved. However, general relativity suggests that anything that falls into a black hole is lost forever, swallowed by the singularity and erased from existence. This apparent contradiction, the potential loss of information in a black hole, has troubled physicists for decades. Gravastars offer a potential solution to this cosmic puzzle. Because gravastars lack a singularity, the point of infinite density, where information is thought to be destroyed in a black hole, they provide a way for information to be preserved. Instead of being crushed out of existence, information falling into a gravastar would be encoded on the surface of the exotic matter shell. Imagine a cosmic message board, a spherical surface where information is inscribed rather than destroyed. This information could, in theory, be retrieved, although the process would likely be incredibly complex and challenging, pushing the limits of our technological capabilities. The possibility that gravastars could resolve the information paradox is one of the most exciting aspects of this theoretical concept. It highlights the potential of gravastars to bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that have long resisted unification. Section 5. Listening for gravastars, the music of gravity waves. Detecting gravastars directly is a daunting task, but not entirely impossible. One promising avenue lies in the realm of gravitational waves, ripples in the fabric of space-time, generated by the acceleration of massive objects. These cosmic tremors, first predicted by Einstein's theory of general relativity, offer a new window into the universe's most violent and energetic events. When massive objects like black holes or neutron stars collide, they generate powerful gravitational waves that propagate outward at the speed of light. These waves carry with them a wealth of information about the objects that created them, their masses, spins, and even the properties of the extreme environments in which they formed. Gravastars, too, are predicted to generate gravitational waves, and these waves could hold the key to their detection. The gravitational wave signature of a gravastar would be distinct from that of a black hole, providing a way to distinguish between these two cosmic heavyweights. For example, when two gravastars collide, they would generate a characteristic ring-down signal, a series of diminishing vibrations that carry information about the object's size and shape. The ring-down signal of a gravastar would be different from that of a black hole, allowing us to potentially identify these exotic objects from their gravitational wave fingerprints. The recent advancements in gravitational wave astronomy, with the advent of detectors like LIGO and Virgo, have opened up a new era of discovery, allowing us to listen to the universe's symphony of gravity waves. As these detectors become even more sensitive, we might soon be able to detect the subtle but telltale signatures of gravastars, providing concrete evidence for their existence and revolutionizing our understanding of the cosmos.